Welcome back to the Walking Clearwater Physics Textbook podcast series. I am your host VB Kataria, and today we will be doing chapter 13 of Physics Textbook, which is Nuclei. So let's dive in. 13.1 Introduction. In the previous chapter, we have learned in this previous means chapter 12, which is atoms, and which we will be covering further, but in the series. But right now, let's continue this one. In the previous series, we have learned chapter. We have learned that in every atom, the positive charge and mass are densely concentrated at the center of the atom, forming its nucleus. The overall dimensions of a nucleus are much smaller than those of an atom. Experiments on scattering of alpha particle demonstrated that the radius of nucleus was smaller than the radius of an atom by a factor of about 10 raised to power 4. This means that the volume of a nucleus is about 10 raised to power minus 12 times the volume of an atom. In other words, an atom is almost empty. If an atom is enlarged to the size of a classroom, the nucleus would be the size of a pinhead. Nevertheless, the nucleus contains more than 99.9% of the mass of an atom. Does the nucleus have a structure just as the atom does? If so, what are the constituents of the nucleus? How are these held together? In this chapter, we shall look for answers to such questions. We shall discuss various properties of nuclei, such as their size, mass, and stability, and also associated nuclear phenomena such as radioactivity, fission, and fusion. 13.2 Atomic masses and composition of nucleus. The mass of an atom is very small compared to kilogram. For example, the mass of carbon atom C12 is 1.992647 into 10 raised to power minus 26 kilogram. Kilogram is not a very convenient unit to measure such small quantities. Therefore, a different mass unit is for expressing atomic masses. The unit is atomic mass unit U, defined as 1/12 of the mass of carbon C12 atom. According to this definition, 1 U is equal to mass of 1 C12 atom divided by 12 is equal to 1.992647 into 10 raised to power minus 26 kilogram divided by 12 is equal to 1.660539 into 10 raised to power minus 27 kilogram. The atomic masses of various elements expressed in atomic mass unit U are close to being integral multiples of the mass of hydrogen atom. There are, however, many striking exceptions to this rule. For example, the atomic mass of chlorine atom is 35.46 U. Accurate measurement of atomic masses is carried out with a mass spectrometer. The measurement of atomic masses reveals the existence of different type of atoms of same element which exhibit the same chemical properties but differ in mass. Such atomic species of the element differing in mass are called isotopes. In Greek, isotope means the same place, i.e., they occur in the same place in the periodic table of elements. It was found that practically every element consists a mixture of several isotopes. The relative abundance of different isotopes differs from element to element. Chlorine, for example, has two isotopes having masses 34.98 U and 36.98 U, which are nearly integral multiples of the mass of hydrogen atom. The relative abundances of the isotopes are 75.4% and 24.6% respectively. Thus, the average mass of chlorine atom is obtained by weighted average of the masses of two isotopes, which works out to be 75.4 into 34.98 plus 24.6 into 36.98 divided by 100 is equal to 35.47 U, which agrees with the atomic mass of chlorine. Even the lightest element, hydrogen, has three isotopes having masses 1.0078 U, 2.0141 U, and 3.0160 U. The nucleus of lightest atom of hydrogen, which has a relative abundance of 99.985%, is called the proton. The mass of proton is MP is equal to 1.000727 U is equal to 1.67262 into 10 raised to power minus 27 kg. This is equal to the mass of hydrogen atom is equal to 1.00783 U minus the mass of a single electron Me is equal to 0.00055 U. The other two isotopes of hydrogen are called deuterium and tritium. Tritium nuclei, being unstable, do not occur naturally and are produced artificially in laboratories. The positive charge in the nucleus is that of the proton. A proton carries 1 unit of fundamental charge and is stable. It was earlier thought that the nucleus may contain electrons, but this was ruled out later using argument based on quantum theory. All the electrons of an atom are outside the nucleus. We know that the number of these electrons outside the nucleus of atom is Z, the atomic number. The total charge of the atomic electrons is minus Ze, and since the atom is neutral, the charge of the nucleus is plus Ze. The number of protons in the nucleus of the atom is described exactly Z, the atomic number. Discovery of neutrons. Since the nuclei of deuterium and tritium are isotopes of hydrogen, they must contain only one proton each, but the masses of the nuclei of hydrogen and deuterium and tritium are in the ratio 1 ratio 2 ratio 1 is to 2 is to 3. Therefore, the nuclei of deuterium and tritium must contain, in addition to protons, some neutral matter. The amount of neutral matter present in the nuclei of those isotopes, expressed in unit of mass of a proton, is approximately equal to 1 and 2 respectively. This fact indicates that nuclei of atoms contain, in addition to protons, neutral matter in multiples of a basic unit. This hypothesis was verified in 1932 by James Chadwick, who observed the emission of neutral radiation when beryllium nuclei were bombarded with alpha particles. Alpha particles are helium nuclei to be discussed. Are helium nuclei to be discussed later in a section. It was found that this neutral radiation could knock out protons from light nuclei such as those of helium, carbon, and nitrogen. The only neutral radiation known at that time was photons. The electromagnetic radiation application of those principles of conservation of energy and momentum showed that if the neutral radiation consisted of photons, the energy of photons would have to be much larger than is available from the bombardment of beryllium nuclei with alpha particles. The clue to this puzzle was Chadwick satisfactorily solved was to assume that the neutral radiation consists of a new type of neutral material called neutrons. From conservation of energy and momentum, he was able to determine the mass of new particle as very nearly the same as mass of proton. The mass of neutron is known to a high degree of accuracy. It is Mn is equal to 1.00866 U is equal to 1.6749 into 10 raised to power minus 27 kg. Chadwick was awarded the Nobel 1935 Nobel Prize in Physics for the discovery of a neutron. A free neutron, unlike a free proton, is unstable. It decays into a proton and electron and an antineutrino, another elementary particle, and has a mean life of about 1000 seconds. It is, however, stable inside the nucleus. The composition of nucleus can now be described using the following terms and symbols. Is atomic number is equal to number of protons. N is equal to neutron number is equal to number of neutrons. A is equal to mass number is equal to Z plus N is equal to total number of protons and neutrons. One also uses the terms nucleon for a proton or a neutron. Thus, the number of nucleons in an atom is its mass number A. Nuclear species or nuclides are shown by notation X superscript A subscript Z, where X is the symbol of the species. For example, the nucleus of gold is denoted by 197 Au79. It contains 197 nucleons, out of which 79 are protons and rest 118 are neutrons. The composition of isotopes of an element can now be readily explained. The nuclei of isotopes given an element must contain the same number of protons but may differ from each other in the number of neutrons. Deuterium 2H1, which is an isotope of hydrogen, contain one proton and one neutron. Its other isotope, tritium 3H1, contains one proton and two neutrons. The element gold has 32 isotopes ranging from A is equal to 173 to A is equal to 204. We have already mentioned that chemical properties of elements depend on their electronic structure. As the atoms of isotopes have identical electronic structure, they also have identical chemical behavior and are placed in the same location in the periodic table. All nucleides with the same mass number A are called isobars. For example, the nucleides 3H1 and 3He2 are isobars. Nucleides with the same neutron number N but differ from atomic number Z, for example 198 Hg80 and 197 Au79, are called isotons. 13.3 Size of the nucleus. As we have seen in chapter 12, Rutherford was the pioneer who postulated and established the existence of atomic nucleus. At Rutherford's suggestion, Geiger and Marchand performed their classic experiment on the scattering of alpha particles from thin gold foils. Their experiment revealed that the distance of closest approach to a nucleus of an alpha particle of kinetic energy 5.5 MeV is about 4 into 10 raised to power minus 14 meter. The scattering of alpha particle by gold sheet could be understood by Rutherford by assuming that the Coulomb repulsive force was solely responsible for scattering. Since the positive charge is conformed to the nucleus, the actual size of the nucleus has to be less than 4 into 10 raised to power minus 14 meter. If we use alpha particle of higher energies than 5.5 MeV, the distance of closest approach to the gold nucleus will be smaller, and at some point the scattering will begin to be affected by short-range nuclear forces and differ from Rutherford's calculations. Rutherford's calculations are based on pure Coulomb repulsion between the positive charge of the alpha particle and the gold nucleus. From the distance at which deviations set in a nuclear sizes can be inferred by performing scattering experiment in which fast electrons instead of alpha particle are projectiles that bombarded targets made up of various elements. The sizes of nuclei of various elements have been accurately measured. It has been found that nucleus of mass number A has its radius r is equal to r naught a raised to power 1 by 3. where R naught is equal to 1.2 into 10 raised to power minus 15 meter is equal to 1.2 femtometer. 1 fm is equal to 10 raised to power minus 15 meter. This means the volume of the nucleus, which is proportional to R cube, is proportional to A. Thus, the density of nucleus is constant independent of A. For all nuclei, different nuclei are like a drop of liquid of constant density. The density of nuclear matter is approximately 2.3 into 10 raised to power 17 kg per meter cube. This density is very large compared to ordinary matter, say matter which is 10 raised to power 3 kg per meter cube. This is understandable, as we have already seen that most of the atom is empty. Ordinary matter consisting of atoms has a large amount of empty space. 13.4 Mass energy and nuclear binding energy. 13.4.1 Mass energy. Einstein showed from his theory of special relativity that it is necessary to treat mass as another form of energy. Before the advent of this theory of special relativity, it was presumed that the mass and the energy were conserved separately in reaction. However, Einstein showed that the mass is another form of energy, and one can convert mass energy into other forms of energy, say kinetic energy and vice versa. Einstein gave the famous mass energy equivalence relation, E is equal to mc square. Here, the energy equivalent of mass m is related to above equation, and c is the velocity of light in vacuum, and approximately equal to 3 into 10 raised to power 18 meter per second. Experimental verification of Einstein's mass energy relation has been achieved in the study of nuclear reactions amongst nucleons, nuclei, electrons, and other more recently discovered particles. In a reaction, the conservation law of energy states that the initial energy and the final energy are equal provided the energy associated with the mass is also included. This concept is important in understanding nuclear masses and the interaction of nuclei with one another. They form the subject matter of the next few sections. 13.4.2 Nuclear binding energy. In section 13.2, we have seen that nucleus is made up of neutrons and protons. Therefore, it may be expected that mass of the nucleus is equal to the mass of its individual proton and neutrons. However, the nuclear mass m is found to be always less than this. For example, let us consider 1608 and a nucleus which is 8 neutrons and 8 protons. We have mass of 8 neutrons is equal to 8 into 1.00866 U. Mass of 8 protons is equal to 8 into 1.00727 U. Mass of 8 electrons is equal to 8 into 0.00055 U. Therefore, the expected mass of 1608 nucleus is equal to 8 into 2.01593 U is equal to 16.12744 U. The atomic mass of 1608 found from mass spectroscopy experiments is seen to be 15.99493 U. Subtracting the mass of 8 electrons, 8 into 0.00055 U. From this, we get experimental mass of 1608 nucleus to be 15.99053 U. Thus, we find that the mass of the 1608 nucleus is less than the total mass of its constituents by 0.13691 U. The difference in mass of nucleus and its constituents delta m is called the mass defect and is given by delta m is equal to z into mass of protons plus a minus z into mass of neutrons minus m. What is the meaning of this mass defect? It is here that Einstein's equivalence of mass and energy plays a role. Since the mass of oxygen nucleus is less than the sum of masses of its constituents, 8 protons and 8 neutrons in unbound state, the equivalent energy of oxygen nucleus is less than that of the sum of equivalent energies of constituents. If one wants to break the oxygen nucleus into 8 protons and 8 neutrons, this extra energy delta mc square has to be supplied. This energy required Eb is related to the mass defect by Eb is equal to delta mc square. If a certain number of neutrons and protons are brought together to form a nucleus of certain charge and mass, an energy Eb will be released. In the process, the energy Eb is called binding energy of the nucleus. If we separate the nucleus into its nucleons, we would have to supply a total energy to Eb to those particles. Although we cannot tear apart nucleus in this way, the nuclear binding energy is still a convenient measure of how well a nucleus is held together. A more useful measure of binding between the constituents of nucleus is binding energy per nucleon (EBN), which is the ratio of binding energy Eb of a nucleus to the number of nucleons A in that nucleus. EBN is equal to Eb by A. We can think of binding energy per nucleon as average energy per nucleon needed to separate a nucleus into its individual nucleons. Figure 13.1 is a plot of the binding energy per nucleon EBN versus the mass number A for a large number of nuclei. Figure 13.1, the binding energy per nucleon is function of mass number. We notice the following main features of the plot. 1. The binding energy per nucleon EBN is practically constant, i.e. practically independent of atomic number for nuclei of middle mass number 30 from A varying from 30 to 170. The curve has maximum of about 8.75 MeV for A is equal to 56 and has a value of 7.6 MeV for A is equal to 238. EBN 2. EBN is lower for both light nuclei A greater than 30, and A less than 30, and heavy nuclei A greater than 170. We can draw some conclusions from these two observations. The force is attractive and sufficiently strong to produce a binding energy of few MeV per nucleon. The constancy of binding energy in the range 30 A7 170 is a consequence of the fact that nuclear force is short range. The consider a particular nucleon inside sufficiently large nucleus. It will be under the influence of only some of its neighbors, which come within the range of nuclear force. If any other nucleon is at a distance more than range of nuclear force from the particular nucleon, it will have no influence on the binding energy of the nucleon under consideration. If a nucleon can have a maximum of p neighbors within the range of nuclear force, its binding energy would be proportional to p. Let the binding energy of the nucleus be pk, where k is constant, having the dimensions of energy. If we increase a by adding nucleons, they will not change the binding energy of a nucleon inside. Since most of the nucleon in a large nucleus reside inside it and not on the surface, the change in binding energy per nucleon would be small. The binding energy per nucleon is constant and is approximately equal to pk. The property that a given nucleon influences only nucleons close to it is also referred to as saturation property of nuclear force. A very heavy nucleus, say A is equal to 240, has lower binding energy per nucleon compared to that of nucleus with A is equal to 120. Thus, if a nucleus A is equal to 240 breaks into two A is equal to 120 nuclei, nucleons get more tightly bound. This implies energy would be released in the process. If it has very important implications for energy production in through fission, to be discussed later in section 13.7.1. For consider two very light nuclei, A is less than equal to 10 joining to form a heavier nucleus. The binding energy per nucleon of the fused heavier nuclei is more than the binding energy per nucleon of the lighter nuclei. This means that the final system is more tightly bound than the initial system. Again, energy would be released in such a process of fusion. This is energy produced of sun, to be discussed later in section 13.7.2. 13.5 Nuclear force. The force that determines the motion of atomic electrons is thus familiar to Coulomb's force. In section 13.4, we have seen that for average mass nuclei, the binding energy per nucleon is approximately 8 MeV, which is much larger than the binding energy in atoms. Therefore, to bind the nucleus together, there must be a strong attractive force of totally different kind. It must be strong enough to overcome the repulsion between the positively charged protons and bind both protons and neutrons into tiny nuclear volume. We have already seen that the constancy of binding energy per nucleon can be understood in terms of its short range. Many features of the nuclear binding force are summarized below. These are obtained from variety of experiments carried out during the 1930 to 1950. 1. The nuclear force is much stronger than the Coulomb force acting between charges or the gravitational forces acting between masses. The nuclear binding force has to dominate over the Coulomb repulsive force between protons inside the nucleus. This happens only because of the nuclear force is much stronger than the Coulomb force. The gravitational force is much weaker than even the Coulomb force. 2. The nuclear force between two nucleons falls rapidly to zero as the distance is more than a few femtometers. This leads to saturation of forces in a medium or a large sized nucleus, which is the reason for constancy of binding energy per nucleon. A rough plot of potential energy between two nucleons as a function of distance is shown in the figure 13.2. Figure 13.2. Potential energy of a pair of nucleons as a function of their separation. For a separation even greater than R naught, the force is attractive. For separations less than R naught, the force is strongly repulsive. The potential energy of a minimum distance R naught of about 0.8 femtometer. This means that force is attractive for distances larger than 0.8 femtometer and repulsive if they are separated by distance less than 0.8 femtometer. 3. The nuclear force between neutron, and proton is approximately the same. The nuclear forces does not depend on the electric charge. Unlike Coulomb's law or the Newton's law of gravitation, there is no simple mathematical form of the nuclear force. 13.6 Radioactivity. A. H. Becquerel discovered radioactivity in 1896 purely by accident. While studying the fluorescence and phosphorescence of compounds irradiated with visible light, Becquerel observed an interesting phenomenon. After illuminating some pieces of uranium potassium sulfide with visible light, he wrapped them in black paper and separated the package from photographic plate by a piece of silver. When after several hours of exposure the photographic plate was developed, it showed blackening due to something that must have been emitted by compound and was able to penetrate both black paper and the silver. Experiments performed subsequently showed that radioactivity was a nuclear phenomenon in which an unstable nucleus undergoes a decay. This is referred to as radioactive decay. Three types of radioactive decay occur in nature. One, alpha decay, in which helium nucleus for He2 is emitted. Two, beta decay, in which electrons are or positrons, particles with same masses as electrons but with a charge exactly opposite to that of electron, are emitted. 3. Gamma decay, in which high energy, hundreds of kilo electron volt or more photons are emitted. Each of these decay will be considered in subsequent subsections. 13.7 Nuclear energy. The curve of binding energy per nucleon EBN given in figure 13.1 has a long flat middle region between A is equal to 30 and A is equal to 170. In this region, the binding energy per nucleon is nearly constant, is 8 MeV. For the lighter nuclei region A less than 30, and for heavier nuclei region A greater than 170, the binding energy per nucleon is less than 8 MeV, as we have noted earlier. Now, the greater binding energy, the less is the total mass of a bound system, such as a nucleus. Consequently, if nuclei with less total binding energy transform to nuclei with greater binding energy, there will be a net energy release. This is what happens when a heavy nucleus decays into two or more intermediate mass fragments, fission, or when the light nuclei fuse into heavier mass, fusion. Exothermic chemical reactions underline conventional energy sources such as coal or petroleum. Here, the energy is involved in the range of electron volts. On the other hand, in nuclear reaction, the energy release is of the order of mega electron volt. Thus, for the same quantity of matter, nuclear sources produce a million times more energy than a chemical source. Fission of 1 kilogram of uranium, for example, generates 10 raised to power 14 joule of energy. Compare it with burning 1 kg of coal, that gives 10 raised to power 7 joule. 13.7.1 Fission. New possibilities emerge when we go beyond natural radioactive decays and study nuclear reactions by bombarding nuclei with other nuclear particles such as proton, neutron, alpha particle, etc. A most important neutron-induced nuclear reaction is fission. An example of fission is when a uranium isotope 235U92 bombarded with a neutron breaks into two intermediate mass nuclear fragments. 1 and 0 neutron plus 235U92 gives 236U92 gives 144 barium 56 plus 89 kryptonite 36 plus 310N, which is 3 neutron. The same reaction can produce other pairs of intermediate mass fragments. 01N plus 235U92 gives 236U92 gives 133Sb 51 plus 99Nb 41 plus 410N. Or other example, 10N plus 235U92 gives 140Xc 54 plus 94Sr 32 plus 210N. The fragment products are radioactive nuclei. They emit beta particles in succession to achieve stable end products. The energy released, the Q value in the fission reaction of nuclei like uranium, is one of the order of 200 MeV for per fissioning nucleus. This is estimated as follows. Let us take a nucleus with A is equal to 240 breaking into two fragments, each of A is equal to 120. Then EBN for A is equal to 240 nucleus is about 7.6 MeV. EBN for 2 A is equal to 120 fragments nuclei is about 8.5 MeV. Gain in binding energy for nucleon is about 0.9 MeV. Hence, the total gain in binding energy is 240 into 0.9 or 216 MeV. This disintegration energy in fission events first appear as the kinetic energy of fragments and neutrons. Eventually, it is transferred to the surrounding matter, appearing as heat. The source of energy in nuclear reactor which produce electricity is nuclear fission. The enormous energy released in an atom bomb comes from uncontrolled nuclear fission. 13.7.2 Nuclear fusion. Energy generation in stars. When two light nuclei fuse to form larger nucleus, energy is released. Since the larger nucleus is more tightly bound, as we seen from the binding energy curve in figure 13.1, some examples of such energy liberating nuclear reactions are 1H1 plus 1H1 gives 2H1 plus electron plus V plus 0.42 MeV. In the first reaction, two protons combine to form a neutron and a positron with release of 0.42 MeV energy. In reaction 13.13b, two neutrons combine to form the light isotope of helium. In reaction 13.13c, the neutrons combine to form a triton and proton. For fusion to take place, the two nuclei must come close so that attractive short-range nuclear forces able to affect them. However, since they both are positively charged particles, they experience Coulomb repulsion. They therefore must have high energy to overcome this Coulomb barrier. The height of the barrier depends on the charges and radii of two interacting nuclei. It can be shown, for example, that the barrier height of for two proton is about 400 keV and is higher for nuclei with higher charges, we can estimate temperature at which two protons in a proton gas would averagely have enough energy to overcome the Coulomb barrier. 3 by 2 k T is equal to K, about 400 keV, which gives T about almost equal to 3 into 10 raised to power 9 Kelvin.